So I hope you folks had a good weekend and holiday. It's good to be able to see you. Unfortunately, Wade was blocked by snow. Some areas of the north got quite heavy amounts of snow, really straining the trees, and so the roads were closed, and he wasn't able to be here. But we won't let that deter us. We're going to be discussing some of the material explored in those videos. So what did the videos involve? Anyone? Give me one or two things there. Pius, yeah.
Diagrams.
Okay. Okay. There was recent video on stock and flow diagrams. That's good. Other things? Yes, Johnny.
We've got delays.
Delays. Good. And Liam. Yeah, target follows. Excellent. First order. Anyone else? Yes. There's a proximity to an Eric, but you're not Eric. So I give up. Alex, thank you. Hazard rates? Okay. They both asked to like the 4-letter name starting with a vowel. Pocket. And so forgive me. So hazard rate, yeah, hazard rate. Excellent. What is a hazard rate? What's another description for a hazard rate? Ooh. A hazard rate is a probability per unit time. It's not just a probability. And why do I what's one difference between it and a probability? What's one sort of thing that holds true for a probability but doesn't hold true for a hazard rate? Okay, I'm gonna, because you already spoke up this term, I love the interaction, but I'm gonna call on Jihan. If you guys know less than or equal to 1. Both of them are greater than or equal to 0. That's true for both of them. The probability per unit time is also greater than or equal to 0, but probability has to be less than or equal to 1. Probability per unit time can be more than 1. So suppose we have a first order delay here. I'll try to alternate between these out of fairness. Suppose we have a first order delay here. And I have a certain hazard rate, a certain chance per unit time, probability per unit time of proceeding alpha. First of all, if this stock is X, what's the formula for this flow? Yeah, or I'll say alpha X. And with the constant at first. So it'd be like 2 times X or 1.5 times X or whatever. Okay, that's good. So what would it mean if this hazard rate were, let's say, 2? What would that mean? What you might think that if there's still a probability, this wouldn't be a legitimate value here, but it's not a probability, it's a probability per unit time. So what would the implications be if this were 2? What would the average time in the stock be? So there was a hand back there. It said, yes. So I'm tempted to say Elliot. Okay. Sorry, it has to the same bin. Not the four-letter bin, no. 4-letter party with a vowel. Not an Elliot? No. Does it have an L in it? Nope. Oh my goodness. Okay. I've got to reboot my brain. So what is it? Aiden. Aiden. How could I Okay, forgive me. Yes, Aiden, yes.
Will double the current stalk to the next output.
So it will what?
Double the stalk leading into the next output.
Okay, that is true. The value of this flow will at a technical level be twice this value, but the value of this flow is actually of different dimension than this. This flow is like, if this is measured in people, this would be people per unit time. So it's actually not something you want to kind of get involved. You can't really legitimately compare a value measured in, people per unit time with a value measured in people. That'll be like saying, is 1 square meter bigger than 0.5 0.5 meters. It's a different sort of unit system. It's a different sort of dimension, and you can't compare them. They're incommensurate. Not one is neither bigger than or less than the other, and it can't be equal to the other. Just like if you have a apartment of 1,000 square feet, you can't say, well, that's bigger than a yard or something like that, because it's a different sort of unit. So I don't want to encourage. It is true that numerically this will be twice that, but I feel uncomfortable like comparing it numerically with this. So, but one other thing is true. I appreciate it in speaking up. If this value is 2, how long do we spend on average in this stock? And I'm going to ask back there, okay, you're going to have to help me with your name. This is like a wipeout. Wade didn't, thank goodness, Wade stayed at home and he didn't wipe out on the road, and I'm wiping out in my classroom, even without snow. So, remind me your name? No, yes. Happy. Yeah, so if the time units were days, the average time here, the mean time here, would be half of a day, 1/2. And that reflects the fact that we could just as well phrase this first order delay with a stock and a flow out with a mean time, call it tau here. It also depends on the value of the stock. And what would the formula be here? What would the formula be if we gave this the same first order delay, if we phrased it this way in terms of a mean time? Matthew, yes. Excel. Yeah. So for this, the equivalent value, if you have chance per unit time of leaving of 2, the equivalent value for the average time in the stock, as Nolan told us, is 1/2. And if you divide X by 1/2, you get 2 times X, right? Like it's going to be the same. This is just a synonymous way to put it. This is just it's 2 sides of the same coin. This and this are numerically going to give numerically identical outputs, because, I mean, not to put too fine a point on it, but multiplying X times alpha is equal to X divided by 1/alpha, right? And I'm saying 1/alpha because it's this, it's divided by this. So what I'm telling you is that these are 2 alternative ways Just really draw a cloud in here in a cloudish sort of way. These are two different ways of phrasing a first order delay. What is it that makes it a first order delay? I appreciate Lynn taking notes on this because this is like highly examinable material. This is like highly visible material. Just like 18. Yes, hi, speak on.
At most two stocks.
So it is true it can occur with a stock down here, although that technically is outside the scope of the first order delay. There was another hand up though, Jihan. Yeah, the rate of flow, it not only, so excellent start, it not only depends directly on this, it's proportional to this in some fixed way, like by a constant here, times this. So in other words, the value here is just a constant times that. So given this, you just multiply it by the constant and you get this. It does depend, that's what this, arrow shows, but in principle, you could have many types of dependencies on that. Some with like a chance per unit time of getting infected that varies itself over time. This is a fixed amount of a fixed constant. It's a constant times this, and that's what distinguishes it. So Jihan was right. It's about the flow, and it's about the flow being just a likeness of the stock in the sense that it's the value of the stock times some constant. Okay. Now, you may say, well, why did I say I'm uncomfortable comparing? Well, this constant is what converts between the dimensions. This is the chance per unit time that you will leave the stock. And the same thing here. It's just x divided by a constant, which is constant times x. It's proportional to, like in terms of a content, the value of the flow out is proportional to the value of the stock. Are we okay with that? Man, that's just yearning to be tested. And you can ace it if you abide by my words. Okay. So here we have first order delays. If Pius is right, like sometimes we put a stock here to show what comes in. You tell me, I've been disadvantaging that side. The problem is I have a laptop and the laptop is having power problems. And if I had my druthers, I would unplug it, stride over to this very table and image this board. But I can't because it will not. I mean, the laptop, not me. But I'm going to have to do it there. And I apologize for those on the side. I'm keenly aware that it's disadvantaging you. And I apologize for that. I am trying to show it in the video, and I will take photos of it and post them to the course site forthwith. Okay. Okay. Now you're going to tell me if I start this talk with some number of people in it, you're going to tell me how many people remain in it. Given that we have this chance per unit time, over time, how many people remain here? There's a formula. I'm going to call the number of people here initially, I'm going to call it X0 because in general, I'm going to refer to the number of people in that stock as X of T, X indexed by T. This, for a given time, this will give the number of people in the stock. Are we okay with that idea? Just notationally. So X of 0 will be the initial people in the stock. How does the number of people in the stock change over time? Can you give me a formula for it? I'll give you a hint. It starts with X0, X at times 0, but it changes in a very specific way. I see a hand up from an Eric-like character. Yeah, yeah.
So wouldn't it be x0 minus alpha x0?
That's a good start to start thinking about it. Let's think. So at a given time, at a given point in time, the rate of this flow will be given by alpha times this. So there's a kind of alpha times this that matters in the whole thing, but actually the formula for this doesn't, it's not just minus. I'll give you a hint. It's times something. It's times something. Johnny.
So I'll say x exponent
It has an exponent.
minus alpha times.
Good man. Good man. E to the minus alpha times time. Now, for some of you, this is your friend. It's one of my good friends. But for some of you, this may not be that familiar. So I'm going to draw it out. And this board is becoming admittedly very, very crowded. So what I'm going to do to avoid inflicting grievous disservice to this side of the room, I'm going to draw this thing twice. That's what I'm doing. Anyone object? Okay, I don't see a revolt, so I'm going to do it in front of you. Okay, so it's going to start up here at time. This is time. You go with that? Time going that way. And this is going to be the number of people on the side. You go with this. And the initial value is going to be x of 0. So this is the difference. And it's going to start here. And what's going to happen? Is it going to go up or down with the only one way it can go, and that's down. Although technically if x is 0, but it can't go up. There's no in. Okay. Now, is it going to go down in a straight line? And the answer is no. So what is it going to do if it's not a straight line? Johnny?
Kind of a sharp initial decline.
Sharper initial decline, and then lower, right? Right? Okay. Now, yes, Johnny.
So if there will be a time what first of all is the curve an asymptote or it's gets to 0 at a point.
It heads towards 0 as time grows larger and larger, but it never reaches 0. Never actually reaches. It grows smaller and smaller, exponentially. I mean, remember in the quiz, the very first day of quiz 0, that this is 1 over alpha t, right? As t goes on, this becomes a big thing. It's growing exponentially, and the 1 over it is going to be smaller and smaller, but it never actually goes to 0. Never actually reaches 0. It goes towards 0 for the time. So I promised this side, and indeed, my viewers online, of whom there's exactly one, UJ, that I would draw that here. So it's going to go like this, and my artistic failings are evident in both drawings, but it's going to be x0 times e to the minus alpha t. This is going to be time. Now, I want to ask you, though, So this is number in stock. And we write that as X of T. Are we okay with this? But I want to ask, why does it go down faster initially and then only slower later? Okay, let's see if we can get some extra voices here. I've seen them. There are more people who are at risk of leaving, and each of them has this chance per day or per week, whatever the unit of time is, of leaving. And there's more people at risk. So there's more people to leave. And so the drop on per week basis is going to be larger. If you have 1 billion people in the stock initially, there's going to be a lot of people leaving per week early compared to once you have 10 people. Right? Stands to reason. Right? The number of people in this, the rate of flow is proportional to the number of people in it. So the smaller this value is, the slower the rate of outflow, and the slower it will drop because the speed of drop is given by the what? Speed of the rate of change of a stock is given by its net outflow, yeah. And the net outflow is becoming smaller and smaller as X goes down, right? Right? Now, it's very important to realize that at each point in time, there's some rate of outflow made up for all. At the initial point in time, there were X0 people, and so it's going to be a rate of outflow given by alpha times X0. But as that's flowing out, there are fewer people there, and so you're not going to have X0 people, X of 0 people anymore. You're going to have fewer people, and so the rate of the outflow is going to decrease in the speed with which this drop is going to decrease. Mm-hmm. So this is completely characteristic of a first order delay. And it results from a situation where the outflow is rate proportional to the inflow. Here we're considering no inflow. Okay, if I phrase this instead of in terms of alpha, in terms of a mean time in that stock called tau, kind of written with that kind of curly like T, also called TAW sometimes. North Americans and British folks have different ways of pronouncing it. Include letters, he's just one of them. So what is it? What is it in terms of if I have a mean time in the stock of tau? That's turns out to be one for alpha, but if I phrase this in terms of that, what would the formula be for how it changes over time? I see a hand from Jihan in the corner of my eye. Speak up. You got it. Man, you got it. Really fair. If you think that, well, give a chance for you to comment leaving, we could phrase it in terms of alpha or in terms of tau, and alpha is just 1 over tau to go between them, or tau is just 1 over alpha. That our mean time in the stock is given by 1 over alpha. Or if we have it given, if what we're told is that you spend on average 3 days in the state of where you're infected but not yet infectious, it's called a latent state of infection before you leave. If we represented that with a stock before it leaves, then your alpha is 1/10. So let me see if I could, I don't want this to just seem like bizarre factoids to be memorized. It's far too beautiful to just memorize. I mean, look, if I have a chance per day of leaving or let me put it better put it this way. If I am going to stay in the stock for just 2 days, about how many of the people would you expect would leave in the first day? Anyone? If you're going to stay there, about what fraction would leave in the first day? If they're there on average for 2 days, what fraction do you think would leave in the first day? Well, about half, right? Right? I mean, just think about it sort of at an intuitive level. If people are going to leave just 2 days, about half roughly will leave in the first day. That's X over 2, in other words, will leave. By contrast, if I'm going to leave on average in 10 days, it kind of stands to reason about 10% of the people will leave per day, if you think intuitively, roughly speaking. And I'm saying that's reflected in X over 10, X over the average amount of time, right? 10%, right? X divided by 10 is 10% of X. So what I'm saying is this formula that where you can specify this in terms of X over tau, it has a certain intuition behind it that you should be able to remember. If I spend on average 4 days in the stock before leaving, about 25% will leave per day. So it's X over 4. But the deal is this stock will be dropping over time. So it's not the case that this will be going down in a linear way. It's that it drops faster at first, and then as fewer and fewer people are left, it'll drop slow. Because there's fewer people leaving, the outflow is proportional directly to the inflow. Are you comfortable with this? Are you feeling okay? Silence leaves a lot of uncertainty. Try to emphasize some of the intuition behind that. Anyone want to ask a question about this? Okay. I'm going to take me a picture of this so that I can preserve it for the campus site. Okay, and I'm going to now ask you another way I could specify structurally a first order delay like this. But we're going to focus for this on a case where we do have inflow. So now I'm going to imagine we have an inflow in here given by rate I. And I'm just going to leave I constant for now for simplicity. So you're going to tell me, I hope you're going to tell me, at what value, I'm even phrasing it in a way that invites you to think about it, frame it in a good way. At what value under what conditions will this stock be in equilibrium? If I have a rate in of I, under what conditions will this stock be unchanging? If what, Aiden has his hand up. Yes, young man.
When the rate of outflow is equal to I.
When the rate of outflow is equal to the rate of inflow. So alpha X, this is what we know must obtain if X must hold, if X is constant over time. right? Inflow equals outflow, right? If inflow is greater than outflow, what will the stock be doing? If this were bigger than this, what would the stock be doing? Lynn. Will rise over time. That's exactly right. If the outflow is bigger than the inflow, what would happen? Stock will decline over time. So that's right. And he also knows that. So it's when these two are in balance, when this is equal to this, that the stock is in balance, right? It's when these are equal to each other. The inflow is equal to the outflow. Okay. So what value will X be when this obtains? Like when this happens, what's the value? Remember, the outflow value of this is given by the value of the stock, X. So at what value of X will this hold when X equals what? So you told me this will be in balance when inflow equals outflow. Great. What does that mean? It means alpha X equals I. Great. But what's the particular value of X? I mean, the outflow is alpha X. What's the particular value of X then? If the outflow is equal to this thing times the stock, what's the value of the stock at which the inflow will equal to the outflow? Well, you just solve it by algebra, right? Right? And Matty, do you want to say it? Yeah, so I over alpha. Just divide this by this. So let's think about that. Alternatively, I'm gonna I'll phrase it in terms of this one here. If we have the same inflow, this is just one way to put it. This is just another way to phrase it, rephrase it. Right? So here, the rate of outflow is given by X over tau. The stock will be in balance when I equals X over tau, right? So X over tau equals I. And so what would X be here? Sorry? Yes, tau. So this implies that X equals tau. And yeah, I'm struggling with the name. Give me. This is terrible. Sorry, is it something like Parisha? Okay, Parisha. Okay, thank you. So as Parisha said, you have X of tau times I. So look, I'm going to try to build some intuition for either of these. Look. Perhaps the easiest one is this one here. If we spend an average amount of time tau in here, let's suppose I told you, hey, look, people are coming into the hospital at a rate of 100 per day. 100 people per day are coming into the hospital, coming in these days. 100 per day are coming in. And they stay in the hospital for an average of 2 days each. Then for the hospital to be sort of have outflow equals inflow, well, how many people would be in the hospital? If 100 are coming in per day and they stay 2 days each, how many people are going to be in the hospital at any one time? Sorry? Okay, it's the other way, right? If they stayed 2 days each, if they stayed 1 day each, before leaving, how many will be in the hospital at a given time? If 100 are coming in per day and they stayed only one day, how many would be there at an average time? Yes, so okay, I'm hashing you to the same thing. This is terrible. Okay, I've got a 50% chance of getting this right. Is this in Eric? Okay. Slightly higher. The loon's beak makes it a bit higher, weight or something. Okay, yes, Eric. Yeah, you'd have 100 people because the people that are there are just those that have come in the past day, so to speak. I mean, I'm trying to build some intuition here. So people are staying here only for a day, and people are coming in at 100 per day. On average, you'd have about 100 people in the hospital, right? Because it'd be the people who came in yesterday. If they stayed 2 days, how many would you have on the hospital? Well, there's the people from yesterday and there's the people from the day before. So you'd have how many? 200. If they stay 10 days, you'd have 100 times 10 or 1,000. Does that make sense? So the number of people who are in the hospital at equilibrium, the outflow is equal to the inflow, is equal to tau, the amount of time they spend in there, like 2 times the rate of inflow, 2 times, wow, the truck overcometh. Impressive. Impressive. I hope it wasn't too grueling. 2 hair raising. So I told them, you are spared a wipeout, but I've had like a wipeout on names. It's been like total wipeout when there's not even snow on the ground here. My goodness. So the number of people in the stock is just tau times the rate of inflow. And that makes sense. This is the value of the stock at equilibrium. I want to be clear. That's when it's in balance. Why is it in balance there? Well, it's because there that the rate of the outflow equals the rate of the inflow. I mean, after all, if this is the value of the stock at equilibrium, tau times I, and the outflow is that divided by tau, what's this divided by tau? What is this divided by tau? What is tau I divided by tau? I'll tell you, tau is non-zero. It's greater than 0. So you don't have to worry with divided by 0. If I say it's not a trick question, tau I divided by tau, what do I get? That'll be the rate of outflow is equal to the rate of inflow, right? This is the value of the stock has to be for that divided by tau to equal I, right? That's what this is saying. I mean, hopefully the neurons are firing that you used in algebra class. Many moves ago. Okay. Now, let's do it for this one. How would this be different? What is the value of the stock at which it's in equilibrium? Well, we derived it. It's I over tau. That is the value of the stock, which if you multiply it by alpha is equal to what? I. This is the formula for the rate of outflow. This is the value of the stock at equilibrium. You plug in that value at equilibrium, multiply it by alpha, you get I, which is the value that you have for the rate of inflow. So it's at this value of X that you get the stock in equilibrium. Outflow equals inflow equals I. Does that make sense? And you notice that this is saying like, well, okay, if you have 100 people per day and your chance per day of leaving is 0.5, then you'll have at any one time 100 divided by 0.5 or 200 people there, because there's a chance they'll leave on the first day and there's a chance they'll leave on the second day of roughly. So I'm glossing over things, but I'm giving this intuition for why it's over this. The lower your chance of leaving per day, this is getting really, really small alpha, the equilibrium value of the stock will be getting really, really large because the average time in the stock is just 1 over alpha. Mhm. And I put in the other board and I should dignify it by putting it here. Right? The rate of leaving per unit time is just 1 over the average amount of time in that stock for a first order delay. And the amount of time you spend on average in the stock is just 1 over alpha. They're just, you can phrase it in terms of this, you can phrase it in terms of that. Are we okay with this? Are we feeling comfortable with this? Okay, now I'm going to ask you for this other way of phrasing first order delays. But first, so that I don't inflict insult upon injury, I'm going to take a photo of this so that it is not lost forever in a cloud of top dust. Okay. Okay, now you're going to give me what's the most sacrificial. I think I'll do it. Yeah, I think I'll leave this one up. Fine. Leave this one up and this one will be sacrificed. Okay. Good. Okay. Yeah, I realize I've got to get over there. Maybe I'll start over there and I'll recreate it again. Not too bad. Okay. What's another way? Like a brighter color, worried it don't throw up in there. Probably for those in the back of the room. What's another way of phrasing a first order delay? I'm sorry, I can see. Mean time. What's another way of phrasing it? Presumably. Someone actually mentioned it once you get about the contents of the. I'll give you a hint, it involves a target. Target follower. It's another way of phrasing this. One way is just giving a separate inflow and outflow. The other is in terms of the target follower. What is that? The new number? Okay, there are oscillations that come up with target followers in the context of delays, perception delays, and if time allows, we'll get to that. But first, this is actually a more basic thing, and I think Jihan has right hand on. You got it. Excellent. Okay, so you don't even know. What we have is one up, and there's a thing called target. And there's a gap, and the target gives, it's the target for the value of the stock. It's like target for a value. I'll phrase it that way for X. Okay. So it's not the target for the flow, it's the target for the value of the stock. And And there's going to be a delay as well. A delay, which we're gonna make tau. Don't worry, I'll put it up there. Just a minute. What is the formula going to be for? Do you know? Let's say it. What is it? You got it. T minus, sorry. Target minus X. That's the gap between the target value of the target and the value of X. And yeah, value of this minus X. It's the difference between these two. So if that's positive, it'll want to go up, well, inflow. If it's negative, the target is less than X, this will be negative, and we'll have outflow. Yes, you can have outflow. Stop. Flow is negative. Flow. Divided by this tau, which serves as a delay. So it assesses, hey, how far above my current value is the target? Further it is above, faster it will rise. So it will rise to the value of the target over time. The equilibrium value of this will be the target. It'll be the equilibrium value will stop. Will be the value of it. This will be following the target. And in that video, I gave some demonstration that this is the same as situation where we have an inflow and where we have an outflow. And then we have there's tau. And this is X over tau. We can phrase it in terms of this, and we can phrase it in terms of that. Where target, if we phrase it in terms of this, the equivalent is the target is given by, well, the equilibrium value here. What is the equilibrium value for this? Anyone? What's the equilibrium value? What's the equilibrium value? What's at what value will the stock of the stock will of X will it be in equilibrium? Yes, maybe tau comes on. Okay. Target is tau times I. It's the value of the target. Or equally, you could say if we have a target, you just divide it by tau, and that's our I. So we have something given to us in this form with a given target. We can convert it to this form by just taking the target and dividing it by I. Dividing by tau. So another way to say this would be I equals target. This is just the relationship between the target and the. So if give it to me this way, you should be able to. If I give it to you this way, I phrase target follower, and if the first way, you should be able to convert it to this by taking this target and dividing it by tau and using that as your I. Tau here is just the thing. And you'll notice it's this X over tau is just hiding, and the fact that it's a minus is reflecting it's an output. This is just like the net flow. We have target over tau, that's I, flowing in, and we have X over tau flowing out, hence minus this. This is like net flow here. That's what this flow is. So net flow in this diagram. And that's what. This one, net flow. It's not an W. This is the net flow. This is what's given by this. If we put two flows in one, it's just I minus this, and that's exactly what this is. The target is I. This is another way of phrasing. Are people comfortable with that? So you tell me, I need to go recreate that over there. Maybe I'll use orange just for a little bit of variety. I indicated that I would phrase that here. So here we have this phrased in the earlier way. This is why I left this one up here with malice aforethought. And here I can convert this into one which has value X, which has target. Our target. This is our target. And why can't I draw it out properly? There we go. And the value of this flow is target minus what? Target minus what? X divided by tau. We need a tau. Constant divided by tau. And I was saying, these are just two different ways of phrasing this. Where target, value of the target is just equal to tau times I, the equilibrium value here, or equally, if you give it to me this way, I can turn it into one of these by using the value of the inflow of target divided by tau. Okay, are we okay with this? Okay, so you tell me. Yes, speak on. Yes, Johnny.
What is target minus X?
What is it?
Target minus X. What is that?
It's the gap between the current value of the stock and the value you want to be at. So it's the gap that you need to cover. You need to raise X by that amount to get to target. Right? Or lower, if target is less than X, you need to lower it by that amount. So it's the net change in X you need to accomplish to match target. It's the change you need to realize in the value of X in order to match the target. I hope that's helpful.
And then what is X over tau?
X over tau, well, if we phrased it in this way, it would be inflow. But X over tau, I mean, X over tau is.
So I'm trying to break it down.
Yeah.
To
It's the out. It was the outflow. Excuse me. This is the equivalent of the outflow, right? Yeah. I mean, as if phrased this way, it's the equivalent of the outflow. It's X over tau flows out. So, yeah. I mean, here it's good to think of this as like a gap. You need to close the gap. My colleague Jeff McDonald talks about mind the gap. This is the gap. And this is sort of the amount of time you need to sort of adjust it to that. So this is kind of intuitively an amount per unit time. This has to rise or fall to align with target and times tau. But as it rises, this calculation will be changing and it will adjust that rate. I don't know if that's helpful.
Yeah, so if the target minus X, can I roughly say it is inflow?
I would, well, I mean, this whole value will be, I'm trying to didactically I'm trying to compare and contrast these and say sort of how to translate from one to the other. For this particular characterization, this whole thing, target minus X, quantity divided by tau, that's the rate of inflow here. Like that's the rate of inflow for this one, for this way of specifying. This whole thing value this inflow. But I was saying that I was alluding earlier, trying to help you be more flexible in your thinking, speaking about the class as a whole. In terms of this thing got erased. In terms of like be able to go back and forth between these. And here I is just target divided by tau, and the outflow is just given by this formula here. Yeah. So you could kind of see this whispered to you in the form of this. It's just another way of phrasing this. So let me ask, if you had target, suppose the value of X is currently 100, and you have a value of target of 200. So this will be target is the value of that of target is 200. What will the value of X do over time? Tell me how it will change over time. Tell me how it will change. What will it look? Jihan has her hand up. Yes, Jihan. Excellent. That's exactly right. That's right. It'll rise faster at first and slow down. It'll rise faster because tau minus X is big. Right? And a big gap to close. And the slope of this will be given by target minus X divided by tau. That's the rate of inflow. That's the net flow. So it's the rate of change of the stock. Initially, it's going to change at initial rate of change, which is given by the rate of flow of change. In other words, flow is given by target minus X divided by tau. So the slope of this line is going to be given by target, right? The target minus the value target minus the value of current value of X divided by tau. I mean, in fact, that's all along here. That's true. You consider the value of the target minus the current value of X here, current value of X, target minus that divided by tau. That's the rate of change. So it's higher at first because this gap is bigger, and then it will slow down as target approaches. As X approaches the target. Like this. As X approaches the target, this will become smaller and smaller gaps. The inflow will be less and less. The rate of growth of X will be less and less, and it will approach this. But never, per Johnny's comment, will it ever get exactly to this. It will target it and it will approach it. What if? So that's what I've drawn here, and I'm going to take a photo of that. But out of equity concerns, I'm going to go over to this board, and in this inimitable orange chalk, I'm going to say, what if we had X like that? And here's our initial value of X. Here's our initial X. Call it X0. Right here. You know? And let's suppose I put in a target of this. This is our target. Yeah. What will the value of X do over time here? what will it do? How will it change? I see a Eric. In fact, I think there are two. Yeah, there's a second.
That would be nearer to one product.
Yes, so it'll be going down, and will it go down faster or slower?
Down south.
Fast, because the gap is what target is less than X, so this is really negative. So it'll be dropping, the net flow is negative, so the value of the stock will drop. It will drop fast at first, and then it will approach it. And what, pray tell, if target is zero? Target equals zero, what will it do? Well, it'll drop like what I threw up here before, right? Like e to the minus alpha t, right? If target is zero, it's like having an inflow of what? If target is equal to zero, it's like this value is just 0 minus x over tau. So it's like having this outflow of x over tau with what rate of inflow? If target equals 0, what's the rate of inflow equivalent to that? 0. Yeah, in fact, we put it here, right? If target is 0, well, what's the equivalent rate of inflow? It's that I equals that. Inflow is called I, right? What's the equivalent rate of outflow of inflow if the target is 0? Well, it's 0 divided by tau. Is off, right? It just has to be the case. This has to be. So look, on the final exam, please remember some basic principles. If you frame these in one way, you could reframe them in another. If you forget with one, you can rederive it with the other. More than that, remember the value of the stock is changing over time. So the rate of the outflow here is going to be changing over time. As it comes for why it changes quickly at first and then slowly later. Because it's adjusting to this towards this equilibrium value. There's less and less of a pronounced gap. Are we okay with that? Now, I want to approach this from one more angle because a few minutes are afforded us. This is going to help you in your final two. But nay, it may help you sooner even than the final. Look, we've been talking about these different ways of phrasing first order delays in terms of tau, in terms of alpha. So I'll redraw the one with alpha here. I'll an I here. If I have alpha here, chance per unit time of leaving. This is called X. What's the formula for this outflow? This is a chance per unit time of leaving. Say what? Yeah, alpha times X. If each of these people, 1,000 people, have a chance of 1% each of leaving per day. So 1 over 100. It's about 10 leaving per day initially, right? Each of them has a chance of, if 1,000 is a chance of 1% of leaving, so there's going to be about 10 of them that are going to leave per day, right? 1,000 divided by 100, 1,000 times 0.01, right? They're going to be leaving per day. So it's got to be this, and this is what I want you to think about. Look, the dimension of alpha is probability per unit time. It's 1 over time. So I should have said, look, if I have a stock and a flow, I have a stock and it flows into it and out of it. the value of the stock, if X has a certain dimension, like person, the dimension associated with the flows into and out of it must be whatever that dimension is, say person, whatever the dimension is of the stock, divided by time. Okay. So a value of 1 for the stock could be 1 person. A value of 1 for the flow out or flow in be 1 per unit, 1 person per unit time. And what I'm telling you is the dimension of alpha is 1 over time. So look, the flow has to have dimension person per unit time. So whatever alpha is, it has to have dimension 1 over time because X is of dimension person. So it needs to be multiplied by something up front to convert it from person to person per unit time. So alpha must have a dimension of 1 over time. Similarly, tau, which is given by 1 over alpha, which is something right here. So alpha has a dimension 1 over time. Tau, which is given as 1 over alpha, has a dimension of what? Time. So the dimension of tau, I'm putting it in sort of brackets, we are 1, is equal to time. Here I occlude the camera. Time. So that's why, you know, we divide by tau, right? Because this has to be whatever the dimension is of the stock, say person, the dimension of the flow has to be that divided by time. So you have to divide by a time thing. If you're going to multiply by an alpha, it has to be a 1 over time thing. You multiply by. So please try to avoid the trap that some people fall in the exam where they forget, do I multiply by tau for the outflow or do I divide by tau? Well, look, this thing has to be of dimension, whatever this is, divided by time. So you have to divide by a time, tau, or multiply by a rate per unit time of 1 over time. Now, you may wonder, what is this 1? Well, it's probability. Probability has dimension 1 because it's like number of coin flips that turn up heads divided by number of coin flips. So whether you measure coin flips in 1 by 1 basis or in terms of thousands or millions, it cancels in the top and bottom. So this is probability. Okay, it's a what we call of unit dimension, or some people call it dimensionless. So I'll put it like this, just to emphasize it's a 1, and that means it doesn't depend on our unit system. There are these profound constants that don't depend on our unit system. In fact, when we model the world, we have to be able to model it in a way that it's amenable to, that it's independent of our dimensions. But that's a deeper point we may come to late in the class, if we do at all. So here, the dimension of alpha is 1 over time. And if you remember that, it will help you if you get confused. Is it alpha times x, or is it alpha x divided by alpha? It has to be alpha times x to convert the flow from being a person, that's x, to person per unit. Okay. And similarly, target minus x, target here, value of target is just rate of the inflow, like people per unit time, times some amount of time. So it's going to be people. It's going to be unit people minus people, yeah, divided by tau, yeah, some amount of time. Going to give us the rate of inflow. This person per unit time. So it all adds up dimensionally. And if you can remember that, you'll be better off in avoiding getting confused about the formulas. You'll just see it must be that way for the world to make sense. for the inverse to make sense. And that, with those words, I will close this lecture. Okay, but I will, as promised, post photos